Today we are going to discuss about linear transformation from finite dimensional space to another finite dimensional space. Previously we learned the linear transformation that goes from Rn to Rm. Besides the Rn and the Rm, the column vectors, there are many things out there that are finite dimensional spaces. For example, the collection of polynomials, the space of matrices, and many other spaces, right? And we also have linear transformation between them, but considering them is going to be not convenient as considering the transformation from Rn to Rm. And today we are going to learn a way so that we can identify such linear transformation as transformation from Rn to Rm in some way. So the first thing we are going to learn is how to represent a vector in finite dimensional vector space V as a coordinate vector in Rn. First definition here. If V is an n-dimensional vector space, an order basis of V is actually just a regular basis, being independent and spanning the whole vector space V. The only difference is that now the order between x1 and xn here really matters. So that means if you switch x1 and x2, you will have a different order basis. Because order basis is actually basis, and basis is spanning. So every vectors in V can be expressed as the linear combinations of the vectors in the basis. And because of the independence, this representation, this linear combination is the only one combination you can write. And this uniqueness property comes from the exercise 2.51 that we considered a long time ago. Now, once you can express every vector in V as a unique linear combination of x1, x2 up to xn, keep the order, right? Don't mess up the order of the axis here. Then the scalars associated with each of the vectors x here, c1, c2 up to cn, are called the coordinates of the vector x with respect to the basis B. And then when you arrange these coordinates in a column, then what you end up getting is a column vector. We call this column vector the coordinate vector of x with respect to the basis B. We need to mention about the basis B because it's very important. If you change the basis, if you change the vectors in the basis, you are going to get different coordinates. And we write the square bracket to mean the column vectors or the coordinate of what? Of x with respect to what basis? That's basis B. This column vector is of course in Rn, and so we usually say that, oh well, we have identified x with this column vector in Rn with respect to the basis B. Of course, if you change the basis, then the column vector is going to be different. All right, so here are some examples. Find the coordinate vector for each of the vector below first. In R3, the standard basis is B. That is the collection of three vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1. If you want to find the coordinate of a vector with respect to a basis, the first thing you want to do, as the definition says, you will have to express the vector given to you as a linear combination of the vectors in the basis. So we express x, which is 1, 2, 3, as a linear combination of the three vectors here. So of course, this is very easy, right? This is 1 times 1, 0, 0, plus 2 times 0, 1, 0, and then plus 3 times 0, 0, 1. All right, after you successfully express this as a linear combination, then the scalar will be the coordinates. And if you arrange the scalar in a column, then it represents the coordinate vectors for x with respect to the basis B. The square bracket means the coordinate vectors for the vector x with respect to the basis B. Now, in this case, coincidentally, you can see that the coordinate vector is equal to the vector itself. All right, so this is just a coincidence. Well, there is a fact that in Rn, if we consider the standard basis, then the coordinate vectors with respect to the standard basis of any vector is going to be the same as the vector, but that's got to be the standard basis, and the space got to be the Rn space. Number 2, the vector is still the same, the space still the same, but the basis is different in this case. All right. So first of all, we have to try to represent x as the linear combinations of the vectors in the given basis here. All right, and keep the order, right? So we want to write x 1, 2, 3 as the linear combination. So this is hard to see right away the scalars, right? So let's denote them A, B, and C. The vectors are going to be 1, 1, 1, 1, 1, 0, 1, 0, 0. Of course, this implies that A plus B plus C equals to 1. A plus B equals to 2, and A equals to 3. And you quickly realize that A has to be 3, B has to be -1, and C has to be -1. And so we can write that the coordinate vectors for this vector x in R3 with respect to the basis B given is going to be A, B, C. But A, B, C in this case has been found. So we have 3, -1, -1. And you see right away, when we change the basis, the same vector in the same space will have different coordinates, and the coordinate will be different with the x vector. All right, the x is the triple 1, 2, 3, but its coordinate with respect to the 3 vectors here, that is the basis, is 3, -1, -1. All right, number 3. Now the space is the space of all polynomials whose degree is as most 2, and we consider the standard basis for P2 here. Right. So what is the standard basis for P2? That is the basis that contains the 3 vectors here in order 1, x, and x squared. So P of x that was given to us is 3 minus 2x plus 5x squared. Now it is obvious that if you denote this as P1, P2, P3, then P of x is going to be 3 times P1 plus -2 times P2 plus 5 times P3. And so you have successfully expressed P as the linear combinations of the 3 vectors in the standard basis here. So this implies that the coordinate vector for the vector P, which is the polynomial in this case, and this coordinate is with respect to the standard basis B above, is now actually just the column vector 3, -2, and 5. So here let me discuss a little bit about why this is important. Right. Nowadays we are working mainly with computers. What will computer do if we give it a polynomial? It will just read 3, -2, and 5 and remember them, right? So if you ask it to do some transformation, it will process this number. These numbers will be processed by the computer, and say it will spit out some numbers, say something like 2, negative 1, 3. What does that mean by this? Now on the screen, it will preserve 3 places. So on the screen, it will show you something like this as a pre-format. And then it will automatically fill up this number into the place. And then there you go, you get another polynomial qx after the processing happened. All right, so that's what happened in the computer. So being able to express a finite dimensional vector space as some Rn is very important. So in this case, P2 is kind of associated with the space R3. Right? Every P here will get correspond to some A1, A2, A3. And that is one correspondence. That means you can go from a polynomial to the triple or the coordinate vector. And you can always go from a coordinate vector, just like this, back to a polynomial. Now we are going to do 4. Sometimes considering different bases is going to be good for us, right? Now, if you denote this as the vector P1, P2, P3, the first thing you want to do is to express Px, which is 3 minus 2x plus 5x squared, as a linear combination of P1, P2, P3. But P1 is 1, P2 is x minus 1, and P3 is x minus 1 squared. You distribute the B, you expand the square and distribute the C, and then you group the like terms. What you end up having is that the left-hand side equal to the free coefficients will be A minus B plus C. The coefficient for x is going to be B minus 2C. And the coefficients for x squared is Cx squared. Of course, when the two polynomials are equal to each other, that means that the coefficients will have to be the same. This is equivalent with A minus B plus C equals to 3, B minus 2C equals to negative 2, and C equals to 5. And so you can easily compute A, B, and C. And so from here you can easily write the coordinate vector for the vector P with respect to the basis given, 6, 8, and 5, in that order. So we have seen that we can go from vectors to the coordinate vectors and recover the vector from its coordinate. Well, there's in fact a linear transformation that represents the process that you can go from vector to coordinate vectors back and forth. Let V be a finite dimensional vector space with an order basis B. The transformation that takes any vectors in V into its coordinate vector is called the coordinate transformation for V with respect to the basis, of course, because when you change the basis, you change the numbers, as you have seen in the previous examples. Now, the coordinate transformation is denoted as T, which stands for the word transformation. The C stands for the word coordinate. The B stands for the basis in which you take into consideration. We write the C to mean the coordinate transformation because in the book there is another transformation that they call the point transformation. But in my opinion, we don't need to use more notation here. The coordinate transformation is in fact an invertible linear transformation. So if you want to take the coordinate back to the point or back to the vector, you just do the inverse of the coordinate transformation and you get back to the vector that you started with. We are going to prove the proposition here. All right, let me briefly draw what is going on. So you have the coordinate transformation with respect to a basis B. That will take a vector in V n dimension. That means the target space is going to be Rn. In this V, you have the basis. b of x1, x2, xn. What t does is that it is going to take a vector x and transform it into a coordinate vector with respect to the basis b. All right. So we are going to write TCB applied on the vector x equals to its coordinate vectors. Previously, when we study linear transformation, the vectors in the domain usually is denoted as x, and the vectors that we obtain in the target space would usually be denoted as y. So the y vector is going to be the coordinate vectors after the transformation happened. If we can write x as a linear combination of the vectors in the basis, then the explicit formula for this one would be a1 dot 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 an. All right, so that's what TCB does. Now we are going to prove the linearity. Now, if we want to prove the linearity, we have to first prove that T preserve the addition in V, right? So for any arbitrarily chosen vector x and x prime in V, we need to show that TCB of the sum x plus x prime equals to TCB of x plus TCB of x prime. Because x is in V and B is the basis, we can write x as a1 x1 plus dot 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 plus an xn. Similarly, because x prime is in V and B is the basis, so x prime can be expressed as some scalar a1 prime times x1 plus an prime times the vector xn. This immediately implies that the coordinate for x, or the coordinate vector that corresponds to x with respect to the basis b, is of course a1 dot 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 an. And the coordinate vectors that associated with x prime with respect to the basis b is going to be a1 prime, an prime. Then this implies immediately that if you add their coordinate, then what you are going to get is a1 plus a1 prime dot 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 an plus an prime. What is this one? Well, it's in fact TCB of x, and this is TCB of x prime. Right, so you know that the sum of the two will be explicitly written as this. On the other hand, if we compute x plus x prime, then we are going to have a1 plus a1 prime times x1 plus dot 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 plus an plus an prime times xn. And that implies the fact that the coordinate for the sum vectors with respect to the basis b is going to be, of course, this dot 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 this. And what is this? It's the coordinate transformation that applied on the vector x plus x prime. And you have seen that they are really the same. So TCB of x plus x prime really is equal to TCB of x plus TCB of x prime. And we are done with the first part of the linearity. Similarly, we can easily prove that T preserves the scalar property. And this is going to be given to you as a practice exercise at home to practice writing proof. Now we are going to prove the invertibility. Now remind that if you want to prove that some transformation T from V to W is invertible, you have to prove that the equation Tx equals y has exactly one solution x for any y we consider. We are considering the linear transformation, that is the coordinate transformation between v and Rn. So first we need to show that if we start with a y from Rn, there will be an x, so that TCB, the coordinate transformation with respect to the basis b, is going to take that x into y. So for any y in Rn, y has to be explicitly written as the form y1 up to yn. We are going to construct the x so that its coordinate is exactly the y's value that we have here. So we construct the x to be y1 times capital X1 dot yn times capital Xn. And we have TCB of x being y1 dot yn right away, which is y. So this x is a solution for the equation TCB x equals y. How are we sure that this is the unique solution we can find? First, suppose that we have two possible different answers, and then somehow we prove that they are the same. So suppose that x and x prime can solve the equation TCB x equals y. Then at that time, we have TCB of x equals TCB of x prime equals to the y written explicitly as an n tuple. We know that the TCB is going to bring x to the coordinate with respect to the basis b. So the coordinate of x with respect to the basis b is y1, yn, and that's the same as the coordinate for x prime. But this part implies that x can be expressed as y1 times x1 plus dot 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 plus yn times xn, and this part implies that x prime can also be expressed as the same thing. And so we have successfully proven that x and x prime are the same. So the solution has to be uniquely determined with respect to what? So the coordinate transformation, the thing that takes vector into its coordinate vector, is linear and is invertible, which means you can go back from the coordinate vector and recover the vector at any time you wish. So next is theorem 3.14. Let V be an n-dimensional vector space with a basis B. W be an m-dimensional vector space with the basis B prime. The transformation T from V to W is a linear transformation. Then there exists a unique m by n matrix, capital M, such that when we multiply the matrix M with the coordinate vectors of x, it will bring you to the coordinate vectors of the image Tx. Right. Remember, x is in the domain and Tx is in the target space. So we got to use different bases between them. Sometimes they coincide, but most of the time the bases are different. So if V has a basis B and W has a basis B prime, then every vector in V will have a coordinate, and every vector in W will have a coordinate. The T will take x into Tx, and the coordinate of x will give you the coordinate of Tx after you multiply the matrix A. Well, it's very similar to the matrix representation theorem that we learned before. The fact is that this is just a generalized copy of that theorem. So you have T being the transformation from V to W, right? In V, you have a basis B. Because it's n dimension, you can write x1, x2, dot, 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 xn. In W, we have another basis B prime. Because the dimension of V is n, we can always identify it as Rn, the coordinate vectors. Because the dimension of W is m, we can always identify W as Rm. This is denoted as TCB. This is going to be TCB prime. Right? These are the coordinate transformation. This is the coordinate transformation from V to Rn. And this is the coordinate transformation from W to Rn. This coordinate transformation allows us to go freely back and forth between the two spaces. This is TCB inverse. Then you go from V to W by T, and then you go here to Rn by TCB prime here. All right. So it's like you consider the composition TCB inverse. Then T comes after, and then TCB prime comes after. Because this is linear, T is linear, this is linear. So the composition is a linear transformation. From Rn to Rm. By theorem 3.1 in the previous section, right, when we study about linear transformation from Rn to Rm, there's a matrix. Say previously we used A, but this time we know that this T is a little bit different with the T go directly from Rn to Rm, right? So we use M, capital M, such that M represents the transformation here, right? So which means that if you consider the transformation, then this transformation will behave exactly like the capital M. To make it clear of what we are going to multiply here, well, if you have a vector x, then it is 1 to 1 corresponding to its coordinate vectors. All right. And then this x will be brought into W and become T of x. And the T of x will be uniquely determined by its coordinate in Rm with respect to the basis B prime. So in short, this linear combination, it is going from Rn, that is going to take a column vector into the associate vector and then transform it into W and then take the result into the coordinate in Rm. Right, so it is going to take effect on the coordinate vector x with respect to the B basis. And so M is going to multiply with this column vector. So what is this one? As explained on the diagram, this is the coordinate of the image Tx with respect to B prime. And so we have the representation here. This time M does not represent T directly, right? As you see on the diagram. The M does not represent T directly. It represents T after we compose T with the coordinate transformations appropriately. All right. And then how are we going to find the M here? Well, we are going to play the trick that we have done for many times up to now. Right? We can plug in x being x1, and we are going to have t of x1 with respect to b prime is going to be m times the coordinate of x1 with respect to b. But the coordinate of x1 with respect to the basis b is in fact just 1, 0, dot, dot, 0. And this is going to give you the first column of the matrix M. You can repeat the process. And then up to the last step, when you plug in x being xn, right, you are going to have t of xn with respect to the new basis in W is going to be m times the coordinate of xn with respect to the basis in the domain. And that is going to be m times 0, 0, dot, dot, 1. And this is going to give you the last column of m. All right. And that's what it says in the theorem. Furthermore, if B is the basis containing x1 dot, dot, xn, then the matrix M can be found by first compute T of x1 and then find its coordinate in the basis B prime. That's going to serve as your first column. Then compute T of x2 up to T of xn and find their coordinate with respect to the B prime basis. That will form the next columns until the last column for you. So now we are going to do some computations to demonstrate the idea. In this example, we have the transformation T that goes from V, which is P3 in this case, into W, that is P2. So in V, we have the basis B that contains P1, which is 1, P2, which is x, P3, which is x squared, P4, which is x cubed. Now we know that in order to find the matrix that represents the T, we'll have to first find T of the first vector in the basis B, T of the second vector in the basis B, T of the third, T of the last vector in the basis B. Right. All right, so T of P1. What is the T? T is the differentiation. Well, that means T is just like d dx. So if you differentiate P1, right, or T of 1, so I'm going to write 1. It's like you take the derivative of 1. And that's of course going to be 0. T of x is going to be like the derivative of x. And of course that's going to be 1. T of x squared is d dx of x squared. That's going to be 2x. And T of x cubed, d dx x cubed, that's going to be 3x squared. Next, you know that in W, you have the basis B prime, that is 1x and x squared. Now your next job is to identify what is the coordinate vector for T of 1 with respect to B prime. What is the coordinate vector for T of x with respect to the basis B prime? What is the coordinate vector for T of x squared with respect to the basis B prime? And what is the coordinate vector for T of x cubed with respect to the basis B prime? In order to do so, we of course will have to first represent each of them as the linear combinations of the vectors in the basis B prime here. So it's going to be like 0 times 1 plus 0 times x plus 0 times x squared. And so we have the coordinate of T of 1 with respect to B prime is going to be 0, 0, and 0. This guy is going to be 1 times 1, 0 times x plus 0 times x squared. So with respect to the basis B prime, T of x will be represented as the coordinate vector 1, 0, 0. This is going to be 0 times 1 plus 2 times x plus 0 times x squared. So with respect to b prime, t of x squared is going to be like the column vector 0, 2, 0. And similarly, this is going to be 0 times 1 plus 0 times x plus 3 times x squared. So with respect to b prime, t of x cubed, the last vector would look like 0, 0, 3. According to what we have learned in the theory, this is going to serve as the first column for the matrix M. This is the second column for the matrix M. This is the third column for the matrix M. And this will serve as the fourth column. All right, so the M that represents the T is going to be 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 0, 3. Let's suppose that we were computers. So for example, our owners want us to find the derivative of some polynomials. How are we going to do that? As computers, what we read about polynomial px is its coordinates vector px with respect to the basis b, and we have known that it is going to be 3, negative 2, and 5. So in view of a computer, I will look at this polynomial just as the 3 numbers here in order. And then in order to find the derivative of this polynomial, I was programmed to know that the derivative is in fact just like the matrix multiplication here on the coordinate. So in order to find the p prime, we would first perform the following computation. M multiplied with p of x with respect to the basis b. Why do we need to do so? Because multiplying m with the coordinate of the polynomial p with respect to the basis in the domain is going to give us the coordinate of the derivative, the differentiation, which is t, right, of p of x with respect to the standard basis b prime in the target space. Right? And this is going to be like the coordinate of p prime of x with respect to b prime. Right? So we are going to multiply the matrix M that we were programmed to remember with the coordinate for p of x. So this is like our input. So then we perform the matrix multiplication. Oh, by the way, I made a very common mistake here. Very often we are going to write just 3 coordinates here because what we saw was just 3 coefficients. But in fact, in the domain, we have x cubed as the last vector in the basis. That means that here, although it is not given, but we would understood it as plus 0x cubed. And so what we miss in the coordinate here is 0. So what we are going to get is the following coordinate vectors. So it's going to be negative 2, and then 10, and then 0. And this is going to be like the output. So on the displays, we print out a format. So we write p prime equals to, we are going to leave a blank here, and then plus, we are going to leave a blank, and then x, and then plus, we are going to give a blank, and then x squared. Then we are going to put this one into the first place. We are going to put this one into the second place. And we are going to put this one into the last position. Of course, we can be programmed to do a little bit more step. If we have 0, we can just skip that part. Right? And so this is like negative 2 plus 10x. And let's go back here. If you start with this polynomial and you take the derivative, you're going to get negative 2 plus 10x. That's exactly what is going on here. Now let's consider another example. Find the matrix M for the linear transformation T. Right, the linear transformation T is actually just multiply the matrix here, the 3 by 2 matrix, with the vector x. And the vector x in this case is a 2 by 2 matrix. So in this case, the domain is the collection of all 2 by 2 matrices. The target space is the collection of all 3 by 2 matrices. So if you want to say that this matrix represents the T, you've got to work with a 2 by 1 matrix X. And in the target space, it's gonna be a 3 by 1 column vector. So if you were given M2 by 1, M3 by 1, then this is of course the matrix representation. However, they are matrices, so they got to be something different. And you will be surprised. You have T that goes from M2 by 2 to M3 by 2. Now in M2 by 2, you consider the standard basis. So you know that the standard basis is going to be the following matrices. Now, each of them is considered as a vector. I'm going to denote them as x1, x2, x3, x4. In the target space, you also have a standard basis. In order to find the matrix representation for this transformation T, we have to first compute T of x1, T of x2, T of x3, T of x4. So T of x1 is going to be 3, 2, negative 1, 0, 0, 1. Multiply with x1, which is 1, 0, 0, 0. And so that is going to give you 3, 0, negative 1, 0, 0, and 0. You then compute T of x2, multiply the same matrix given to us with x2. And that is going to be 0, 3, 0, negative 1. Now then you compute T of x3. If you do the computation correctly, you should get 2, 0, 0, 0, 1, 0. And then T of x4. 0, 2, 0, 0, 0, 1. All right, next, we want to express T of x1 as the linear combinations of y1, y2, y3, y4, y5, and y6. The first position is 3. That means you will have to multiply y1 by 3. Right? Luckily, they are the standard basis. Otherwise, we have to solve a system of linear equations to get the coefficients out. Anyway, so that's 3y1. This is 0. That means you multiply y2 by 0 to zero out the number 1 here. So plus 0 y2. All right, and then this position is negative 1, means you have to multiply y3 by negative 1. You multiply y4 by 0. You multiply y5 by 0 as well. You multiply y6 with 0. This implies that the coordinate of T of x1 with respect to B prime is going to be the following vector. So you have 3, 0, negative 1, 0, 0, 0. So you put them in that order into the column. 3, 0, negative 1, 0, 0, 0. Now repeat this process for T of x2. You will find T of x2 being 0y1 plus 3y2 plus 0y3 plus negative 1 y4 plus 0 y5 plus 0 y6. And this implies that the coordinate for t of x2 with respect to the basis in the target space is going to be equal to 0, 3, 0, negative 1, 0, and 0. Similarly, t of x3 is going to be 2 times y1 plus 0 times y2 plus 0 times y3 plus 0 times y4 plus 1 times y5 plus 0 times y6. And so we have the coordinate of t of x3 with respect to b prime is going to be 2, 0, 0, 0, 1, and 0. We repeat this for t of x4, and we are going to have 0 y1 plus 2 y2 plus 0 y3 plus 0 y4 plus 0 y5 plus 1 y6. And so this implies that the coordinate for t of x4 with respect to the basis in the target space is going to be 0, 2, 0, 0, 0, 1. So we know that this is going to serve as the first column for the matrix M. This is going to serve as the second column for the matrix M. This is going to be like the third column for the matrix M. And this is the last column for the matrix M. And so the matrix M is going to be equal to 3, 0, negative 1, 0, 0, 0, 0, 3, 0, negative 1, 0, 0, 2, 0, 0, 0, 1, 0, 0, 2, 0, 0, 0, 1. Right, this is the matrix representation for T. Right, so now let's consider this example. V, that is P2. W is P2 as well. But we are considering two different bases, and they are not the standard basis. And T is the linear transformation here. So the T is going to be the transformation that is going to take or transform a P2 polynomial into a polynomial of degree at most 2. Here we have the basis B for V, and here we have the basis B prime for W. What are they? The basis for B is now 1, x minus 1, and x minus 1 squared. And here in W, the target space, I'm going to use a different color, right? We are going to have the basis B prime that consists of the following vectors: 1, x minus 2, and x minus 2 squared. I'm going to call this the first polynomial. This is the second polynomial, and this is the last polynomial. So T of 1 is going to be x squared 1 double prime, the derivative of 1, and then plus the function. Of course, that is going to be 1. Now, the next step you need to do is to express it as the linear combinations of the bases in the target space. And because this is the number 1, so we are going to have 1 times P1 plus 0 P2 plus 0 P3. And so this immediately implies that the coordinate of T1 with respect to B prime is going to be 1, 0, 0. And this is going to be identified as the first column for the matrix M that we are looking for. Now next we are going to compute T of x minus 1. Right, it's going to be x squared times x minus 1 double prime minus x minus prime prime, and then plus x minus 1. So you're going to get x minus 2. Then next we are going to represent it as the linear combinations of the vectors in the basis of the target space. So that is going to be 0 times p1 plus 1 times p2 and then plus 0 times p3. Right, so here we got luck because the polynomial that we found is exactly the second vector in the basis b prime. That is not always the case, but anyway, that's good for us. We save some time here. So that means the coordinate for t of x minus 1 with respect to the basis of the target space is now obviously 0, 1, and 0. And this, as we know, it will represent the second column of the matrix we are looking for. Next, we are going to compute t of x minus 1 squared. So x squared times the second derivative of x minus 1 squared, and then minus the first derivative of that guy, x minus 1 squared, and then plus the function x minus 1 squared. You are going to get the following. Negative 3 minus 4x plus 3x squared. Next step, we are going to express this as the linear combinations of the vectors in the basis b prime. Now you get something that is obviously not easy to express in terms of p1, p2, and p3. So we want to write negative 3 minus 4x plus 3x squared as a times p1 plus b times p2 plus c times p3. That means we want a, b, c such that a times 1 plus b times x minus 2 plus c times x minus 2 squared equal to the left hand side. Now after you distribute b, expand the square and distribute c, group the like terms and rearrange them, you should get something like this. So a minus 2b plus 4c for the free coefficients. The coefficients for the x would be b minus 4c. And the coefficient for the x squared is going to be c. Now you have two polynomials that are equal to each other. That means the coefficients will have to be the same. So this implies immediately that negative 3 will have to be the free coefficient a minus 2b plus 4c. Negative 4 will be the coefficients for the x, b minus 4c. And 3 is going to be the coefficients for the x squared, which is c. So you use back substitution and you are going to get a, b, and c. C is going to be 3, b being 8, and a is going to be 7. All right, so this implies that the coordinate of t of the third vector with respect to b prime in the target space is going to be 7, 8, and 3. And we know for sure that this is going to be the third column for the matrix that we are looking for. So this implies that the matrix M that we are looking for is going to be 1, 0, 0, 0, 1, 0, and then 7, 8, and 3.